Good day everyone, my name is Erica Pauline Alizaka and together with my groupmates Kuya Riquermi and Kuya Soldia, we will be reporting about district energy conversion systems. So what are district energy conversion systems? District energy conversion systems are centralized energy systems that produce thermal energy, such as heating and cooling, at a single central plant and distribute it through multiple buildings through a series of insulated pipes. Instead of each building having its own boiler or chiller, energy production is shared across a district or a network. In terms of operation, energy is first produced at a central plant, then transported through distribution network, and then finally, it is transferred through individual buildings through heat exchangers. This approach allows buildings to receive heating or cooling without on-site combustion or large mechanical systems. One important advantage of district energy systems is that they enable flexible fuel switching and centralized efficiency improvement. As energy technologies evolve, the central plant can be upgraded without modifying individual buildings, making district energy systems adaptable and future-ready. Resources and inputs for district energy conversion. District energy systems can operate using a wide range of energy sources and feedstocks. Traditional or conventional sources include natural gas-fired central boilers, as well as oil or coal-based plants, which are mainly found in older or legacy systems. So, kanang mga daan-daan na nga mga systems mo pa ni mga gipanggamit nila. In addition, many systems make use of waste heat recovered from power plants, and industrial processes that would otherwise be lost to the environment. So, ang uban pod systems, mugamit pod sila ang mga waste heat and i-recycle nila. So, instead nga ma-waste na siya into the environment, ilang kuhaon para ilang gamiton sa ilahang system. Modern district energy systems increasingly rely on renewable and low-carbon sources. These include biomass boilers, geothermal energy, and solar thermal systems. Natural water bodies such as rivers, lakes, or even seawater are often used for efficient heating and cooling systems, along with waste heat from sources like data center and metro systems. A key feature of advanced district energy systems is their integration with electricity generation through CHP or combined heat and power. CHP plants produce electricity and useful heat at the same time, achieving very high overall efficiencies of between 80 to 90%. This creates a strong coupling between district energy networks and power grid, improving overall energy system performance. Now that we are finished with the introduction, I will now give the floor to Mr. Riquerme for the conversion pathways and system components.
Good day everyone. For this part of the report, I will be discussing district energy conversion systems. These systems provide heating, cooling, and sometimes electricity by producing energy at a central plant and distributing it to multiple buildings through a shared network. District energy systems are important because they improve efficiency, reduce emissions, and support sustainable and urban development. District energy systems start with a central energy plant where heat, cooling, and power are produced. These systems generate steam, hot water, or chilled water at a central plant and then distribute it through a network of underground insulated pipes to buildings in a district. Examples of a centralized technologies include boilers that are fueled by gas, biomass, or waste-to-go energy. Examples of centralized technologies include boilers fueled by gas, biomass, or waste-to-energy sources. Combined heat and power, or CHP, or cogeneration, which produces electrical power and useful thermal energy from the same fuel input. Trigeneration, which adds cooling production to CHP systems. Large-scale heat pumps and other renewable heat sources. Recovery of industrial or urban waste heat to supply the network efficiently. Because many users share the same plant, district systems achieve higher overall efficiency and lower emissions than individual building systems with separate boilers or chillers. District cooling systems. District energy also includes cooling generation. Instead of each building having its own chiller or air conditioning system, chilled water is produced naturally and sent through the same type of underground pipe network used for heating. This setup provides cold water for space cooling and industrial processes, reduce peak electrical demand typically associated with air conditioning, can be powered by waste heat absorption chillers, or integrated with CHP systems to improve overall efficiency. Thermal energy storage. Thermal storage is an important component that enables better use of energy across time. District system can also store hot water, chilled water, or ice, allowing energy to be held during the low demand periods and used during peak demand. This is known as peak shaving, and it helps improve plant efficiency, reduce operating costs, facilitate the integration of variable renewable sources like solar or wind, support flexible system operation through the day. Distribution network and building interfaces. The distribution network consists of underground pipes that carry thermal energy in a closed loop. Supply and return lines circulate steam, hot water, or chilled water to buildings. Heat exchangers at each building separate the district network from the building's internal heating or cooling system while transferring energy. This means individual buildings do not need their own boilers or chillers, use equipment, maintenance, and space requirement. Now, end uses. Once delivered, district energy can serve multiple functions for space heating, domestic hot water, cooling and refrigeration, industrial or process heating. Because the energy is delivered in usable thermal form, buildings connected to a district system have simplified operations and often lower life cycle costs. System integration and optimization. Modern district energy systems are not just about pipes. They are integrated energy infrastructures like cross-section integration, smart operation, and efficiency. Now for cross-section integration, they can be coupled with the electric grid, integration renewable sources like solar, thermal, or geothermal. Take advantage of waste heat from industries or power plants. Combine heating, electricity, and cooling in one optimized network. Now for smart operation and efficiency, advanced controls and optimal scheduling maximize performance. Thermal storage reduce waste operation. Load aggregation allows large central plants to operate more efficiently than many small systems. Together, these strategies reduce fuel use, lower emissions, and increase system resilience compared to separate systems in each building. Application of district energy systems. Heating and hot water supply. District heating networks can serve residential, commercial, and institutional buildings from one central source. This improves both efficiency and reliability compared to standalone systems. Cooling chilled water supply. Similarly, district cooling provides chilled water to multiple buildings, often with higher efficiency and lower peak power demand relative to individual chillers. Combined multi-energy systems. System using CHP or tri-generation supply, like for heat, electricity, and cooling. This improves fuel efficiency and reduce emissions compared to separate heat and power generation. Urban and industrial integration. District systems can use waste heat from factories or power plants and large-scale thermal storage, enabling better use of renewable energy and supporting urban decarbonization goals.
Benefits and challenges. Benefits of district energy systems. High efficiency. Centralized generation often use combined heat and power or waste heat recovery, achieving efficiencies above 80%. Fuel flexibility can integrate biomass, geothermal, solar thermal, industrial waste heat, and other renewables. Scalability and reliability serves entire communities, campuses, or districts with reliable continuous thermal energy. Reduced emissions enables easier decarbonation by transitioning centralized plants to cleaner fuels. Lower life cycle costs, reduced capital and maintenance costs per building, and compared to individual systems. And here is the key challenges. High upfront investment, significant capital required for infrastructure, pipes, plants, and energy transfer stations. Long implementation timeline. Planning, permitting, and construction phases are extensive. Geographic suitability. Most economical in dense urban areas or campuses with high thermal demand. Regulatory and stakeholder coordination requires strong policy support and collaboration between public or private entities. Operational complexity demands advanced control systems and ongoing maintenance for network efficiency. For the conclusion, district energy, a sustainable pathway for urban energy systems. District energy conversion systems represent a proven scalable solution for efficient thermal energy delivery in dense and developing areas. By centralizing production and enabling multi-energy integration, these systems enhance energy security, reduce carbon footprints, and support smart city development. While implementation challenges exist particularly in financing and coordination, the long-term environmental, economic, and social benefits are substantial. Call to action policymakers. Urban planners and energy providers must collaborate to prioritize district energy and sustainable urban development, leveraging modern technology and renewable integration for resilient, low-carbon communities. Thank you.